Jai Hind everyone. My name is Rinki Tyagi, working as an assistant professor in IT department in Ajay Kumar Garg Engineering College. Today this is my fifth lecture on the subject computer organization in architecture. And today we are going to discuss about memory, with that basic concepts of memory, hierarchy of memory, semiconductor RAM memories, 2D and 2.5D memory organization, ROM memory, cache memory, concept and design issues, and performance, what is the cache memory is facing, and basically the address mapping. So we are going to discuss these topics today. First, let us understand what is memory unit. Memory unit stores instructions and data. So in whatever instruction you are writing or whatever instruction you are going to use, you have to store that data into memory. Processor read instruction and read or write data to and from the memory. When processor is reading the data, then the data will be read from the memory, and when the processor is going to write the data, or we can say that when the processor is going to store the data, it will be stored into the memory. And when it will be stored, or when the instruction will be executed, during the execution of a program. During the execution of the program, the instruction will be executed. So in order to read or write to and from a memory, a processor should know the following things. First, address. If you don't know the address, how you will reach on that location in memory where you have to store the data and from where you have to read the data. So this is the most important thing. If you don't have address, you will not reach at that location, because you don't know. There is a bulk amount of data in memory. You don't know what data you will use if you don't have address location. So address is associated with each word location. You have to reach on that address first, then from that address you will read the data, or you will write the data on that address. Processor read or write to and from memory based on the memory address. So as I said, address plays the major role. As you don't have an address, you will not be able to execute your work, or you will not be able to execute your task. You have to access any word location in a short and fixed amount of time based on the address. Like you have to go to your friend's place. If you don't have an address, how you will reach there? First you have to find that address, then only you can reach. So if you have an address, then in very short amount of time, or we can say in fixed amount of time, you will reach on that location in memory and access the data or store the data at the memory location. Second is random access memory, because it provides fixed access time. It is random access memory is basically volatile in nature. When the power goes off, the data is also gone. So this is volatile in nature. This is temporary memory. So it always provides fixed access time independent of the location of the word. RAM doesn't know what will be the location. It will provide the time if you don't have a location, and in that location you have to reach at that address, and in that on that location, if you will not reach in that fixed amount of time, then your operation will not be executed. And the time that is taking in accessing the memory is known as memory access time. So here we know about the three things: that the instruction and data is to be stored in memory first. Second, you need an address to execute the instruction, or to store the instruction or to fetch the instruction. If you don't have an address, then RAM will provide a fixed amount of time. On that time, if you will not be able to reach that address, then your task will not be executed. And the time taking for accessing the memory is known as memory access time. Now moving ahead, memory and processor have to communicate with each other. So there are two types of operation that we are going to perform in that are whether we will read the data from memory, or we will store the data into memory, or we can say write the data into memory. Data can be raw, or data can be meaningful. So the meaningful data is known as information. So we want to access memory as fast as possible, because our time is very precious and costly. So to reduce communication time, a small amount of RAM, that is cache, is used, and cache is tightly coupled with the processor. What is the meaning of this? Why we are using cache? First, let us know the cache is also known as buffer. As we know, the our CPU speed is very high, because time is very important. It is a major factor. We want that our CPU execute as fast as possible, and the processing speed of memory as compared to CPU is very slow, and when the CPU is fetching or giving the data to the memory, there will be a bulk of data will be in a queue, because the speed of memory is very less as compared to the speed of CPU. So to buckle up this speed, buffer known as cache memory is used between processor. Here there is a processor that is known as your CPU, and the buffer that is known as cache memory is used between your main memory and CPU. So CPU will give the data to the cache and will take the data from the cache, and main memory will also give the data to the cache and will take data from the cache memory. So the cache memory is the fastest memory that is working for CPU, as it is matching up the speed of the CPU, and it is also storing the data to send the data to the main memory when main memory will save the previous data. So it is basically the buckling up the speed of CPU and the main memory. So the primary storage of consists of RAM. RAM is basically our cache, or that is fastest and smallest unit, and the second part of the RAM, that is also known as RAM, is slowest memory, and it is known as largest memory also, that is known as our main memory. So primary storage is basically insufficient to store large amount of data and storage. So primary storage can be added if we think that we have 512 MB of RAM and the storage is not enough and we need to store data in TBs, then we can add the RAM, but it will be quite expensive when we are going to increase the size of a RAM, because it is very costly. To store large amount of data on secondary storage devices, there are types of secondary memory, that is your magnetic disk, your tapes, your optical disk, that is your CD-ROM, because they are the slowest memory and also known as the largest memory and also known as cheapest memory devices. So basically what we learned from the whole slide, that the cost of memory unit basically depends on its access time. The lesser the access time, the higher will be the lesser the access time, the higher will be the cost. So moving ahead, so measures for the speed of a memory. What are the measures? On that base we are going to check the speed of our memory. The first measure is elapsed time. So the elapsed time will be taken between when we are initiating the operation and when the operation is complete. Like we are going, this is a memory, like we are going to start the process as 5 millisecond and that operation is completed at 8 millisecond. So this time is known as your elapsed time. This time is known as your elapsed time. So the elapsed time will be 5, 6, 7, 8, that is 3 millisecond. That is 3 millisecond, and the minimum time between the initiation of two successive memory operation is memory cycle. So this is the one operation that is going to perform, and the second operation is performed at 10 millisecond. So these are the two successive operations, and the cycle is created for completing these successive operations is known as your memory cycle time. Generally, the faster a memory system, the costlier it is and the smaller it is, because the cost is the major factor. The smaller the memory, the speedy the memory, the higher will be the cost. So an important design issue is to be provided to provide a computer system with as large as fast a memory as possible. So we want to provide a memory so that our customer can afford its cost, and according to the costing we need to see the size and the speed of the memory also. So we have several techniques to increase the effective size and speed of the memory. First one is, if we want to only increase the speed, then we can add cache memory, and if we want to increase the size, then we can add our virtual memory also. We will study later in our lecture videos about deeply about cache memory and virtual memory. Now, what is the hierarchy for memory? So the level 1 is register. First one is register. These are the smallest memory devices. Registers are basically made up of flip-flops, and one flip-flop can store only one bit of data, either 0, either 1. And registers are made up of only flip-flops. If the size of register is 8-bit, then 8 flip-flops are used for adding a 8-bit of register. So after that, moving downward, we have level 1 cache, then level 2 cache, then main memory, then these are your secondary memory devices. So what is the role? Registers are the fastest memory and the smallest memory, and they reside inside the CPU. Basically, registers are used to store the temporary data that is stored during the computation of an expression. So basically, registers are the fastest memory because CPU don't need to go to the cache or to the main memory. CPU will directly access data from the registers, and these are inside the CPU. So very less time is needed to access registers. Second one is level 1 cache. Level 1 cache is inside the CPU. On processor chip, it is implemented level 1 cache, and it is smallest, fastest and a costly memory. Then after that, level 2 cache. Level 2 cache is between your CPU and your main memory, that worked as a buffer. So it is basically used to buckle up the speed of CPU and the memory, as I told, main memory. Next is, after main memory, you have your secondary devices. Either can be a fixed disk, either can be optical disk, either can be magnetic disk. So what we have seen in this diagram, that the smallest the memory, the costly it is. The smallest the memory, the costly it is. So basically, this is the memory hierarchy. That this is the basic hierarchy, that the access time for registers is basically 1 cycle, and its capacity, these are the basic capacity. This is the basic capacity of a register, that is 1 KB, and registers are managed either by soft compiler. Then we have 3 types of cache, that is level 1, level 2, level 3. Level 1 cache uses 2 to 4 cycle for accessing data, and 32 KB capacity is the 32 KB is the capacity of level 1 cache, and they are managed by hardware. Then it is level 2 cache. They need 10 cycles to access data from memory, and 256 KB is the capacity and managed by hardware. Then next, moving ahead, that we have level 3 cache, and they need 40 cycles to access the data from memory, and 10 MB of data is the capacity of level 3 cache, and level 3 cache is managed by hardware. Then we have our main memory. 200 cycles are needed to access data from main memory. 10 GB is the capacity, and they are managed by your software or rather your operating system. And then flash drive, they need 10 to 100 microseconds, and 100 GB is the capacity and managed by software and operating system. And last one is your hard disk, that is 10 milliseconds is required, 1 TB is the capacity, and software, they are managed by software or operating system. So what this diagram represent, that we have CPU, inside CPU we have registers and level 1 cache. Then we have level 2 cache here between the main memory and the CPU. So CPU can directly access the data from main memory also, but CPU can access the data from cache memory also if there is a problem of speed. Then input output processors are also connected for any input output. There is also a processor that we will study in unit 5 about input output processor, that they are used for peripheral devices basically. And then your secondary memory is there, that is your magnetic tape, hard disk, optical disk, flash drive. And secondary memory is also known as auxiliary memory. So what is the big challenge in the hierarchy of memory? The big challenge is in the design of a computer system. So we need to provide the larger memory. We want that we can provide larger memory with a reasonable speed and at an affordable cost. So there are 2 types of RAM, that is your static RAM and your dynamic RAM. What is the difference between them? The static RAM is very fast, but it is expensive. Why it is expensive? Because a basic SRAM cell has a complex circuit. Its circuit is very complex because there are number of large cells that are implemented on a single chip. Then what about dynamic RAM? Dynamic RAM is simpler basic cell circuit. It is basically a simple cell circuit, and that's why it is very less expensive. But the problem is that they are slower than static RAM. Then why they are used? If we don't have too much, we can't afford too much, our customer can't afford too much, and we have to compromise with the speed, then we can use static RAM, dynamic RAM as compared to static RAM. Then coming towards magnetic disk, storage provided by dynamic RAM is higher than SRAM. as we know that SRAMs are very small and implemented on a single chip. So the storage space of dynamic RAM is very high as compared to SRAM, but it is less than what is necessary because we want speed. Secondary storage such as magnetic disk provide a large amount of storage. So to provide a large amount of storage at a cheapest cost and at a slow rate, we use magnetic disk and they are slower than dynamic RAM. So what is main memory? Basically we have seen that this is your CPU, this is your cache, and then it is main memory. This is cache. CPU can also be directly connected to main memory, and then it is, here it is secondary memory, or you can say auxiliary memory. So basically the main memory lies between the CPU and the secondary memory. Here it is written the main memory lies between the CPU and the secondary memory. So basically it is the central storage unit in a computer where you can store all of your data. If the main memory is full, then we go towards secondary memory. So it is relatively large and fast memory to store programs and data. Basically the principal technology is based on semiconductor integrated circuit. What does it mean? It means that the main memory is made up of semi-integrated ICs. Most of the main memory is basically used by general purpose computer, and it is most of the main memory is made up of RAM, but some portion of memory may be constructed with ROM, because RAM is your random access memory that is volatile, and ROM is your read-only memory where you can store your software that always runs on the back end when you are going to perform your task. So that data that can only be read by the client or that cannot be modified by the client always placed in ROM chip. Originally RAM was used to refer to random access memory. Originally RAM was known as random access memory, but nowadays it is also known as read or write memory. Why it is known as read or write memory? Because here you can manipulate, you can update, you can store your data, you can write your data. But in read only memory, you cannot write any data, you cannot update, you cannot modify, you can only read the stored data. So RAM is used for storing the bulk of the program, but ROM only store that data that is permanently stored and that cannot be updated. So what is the difference between RAM and ROM? The basic difference is it is known as random access memory and it is known as read-only memory. RAM data is basically volatile and the data is present till the power supply is present. ROM data is permanent. It is not volatile in nature, it is permanent in nature, and even if the power supply goes off, the data will not be deleted and data will not be volatile from your system. It will always reside in your system. The RAM data can be read, erased or modified, as I told, as it is a read-write memory. So here we can write data, read data, update data, modify data, but in ROM we can only read the data. We cannot do any modifications in data. RAM is used to store data that CPU needs for current instruction processing, but ROM always stores the data that is used for bootstrapping the computer. So basically the speed of RAM is quite high as compared to the speed of ROM. Here CPU can access data stored on ROM, but the data, if CPU want to access the data that is stored in ROM, then first that data is copied onto RAM, then CPU can only access the data. So CPU can directly access the data from RAM, but if CPU wants to access the data that is stored in ROM, then the data is first copied at RAM, then after that data will be read by the CPU. So the capacity of RAM is large and high, but the capacity of ROM is generally small and low, because we need only few softwares that always run on backend, and that we know how much space we need in ROM. So the size of ROM is generally small. RAM is basically used as CPU cache memory or the primary memory, but the ROM is basically used by your firmwares, your microcontrollers. So basically, as we know that RAM is costly and ROM is cheap. So this is the difference between RAM and ROM. Now the next category of RAM is types of RAM is SRAM and DRAM. So as I told that SRAM is more expensive as compared to DRAM, and SRAM is have high speed than DRAM. Then what are the basic differences between SRAM and DRAM? Let's see the differences first. The SRAM is basically made up of semiconductor memory, but DRAM is a type of random access memory. Here each bit of data is stored in separate capacitor, but here the data is stored in your latching circuit. SRAM uses transistor to store single bit of data, but DRAM uses separate capacitor to store each bit of data. SRAM does not require any refreshment after a period of time to maintain the data, but in DRAM we required periodic refreshment to maintain the charge. What about access time? SRAM has lower access time as it is faster than DRAM, and DRAM has higher access time because it is slow as compared to SRAM. SRAMs are used in cache memory and DRAMs are used in main memory. SRAM structure is more complex than DRAM as there are array of transactions, latches, and cross-coupled inverters that are implemented on a single chip in form of SRAM. But in DRAM, the structure is simple when compared to that of SRAM. Due to complexity of internal circuit, in SRAM, less availability of space is there, as we discuss about the physical space in SRAM, because a number of circuits are on a single chip. So the physical space is less as compared to DRAM. So we got more space in DRAM as compared to SRAM. SRAM require constant power supply. If the power supply goes off, the data will be volatile. DRAM offer reduced power consumption. That's why the information is stored in capacitor. That's why we are using capacitors in DRAM. SRAM generates more heat as compared to DRAM. SRAM is used to create speed sensitive cache, but DRAM is used to create a RAM space. The latency of SRAM is low, the latency of DRAM is high, and SRAM is quite expensive as compared to DRAM. So these are the basic differences between SRAM and DRAM. So, and now coming to the next topic, that is ROM. Now, as we know, ROM is read-only memory. We cannot modify or update data in ROM, and it is less costly as compared to RAM, and less space is required in ROM as compared to RAM. So what are the types of ROM? The first type of ROM is MROM, known as masked ROM. It is the first ROM and it uses hardware devices. It uses hardware devices, and hardware devices uses pre-programmed set of data or instruction, and that's why it is known as masked ROM, and it is inexpensive in nature. Next one is PROM. PROM is known as programmable read-only memory. PROM is read-only memory that can be modified only once by a user. Like you have a memory, you can store data only a single time. So what is the, we can have a small fuses, like we have a fuse. When a fuse got burned, it will be useless. It can be used as only one time, fuse. So when it is programmed only once, after the programming, the data cannot be erased. Next is erasable and programmable read-only memory. Now we are seeing the last one is programmable. Only once you can program the data. After programming, you cannot erase the data. Here, erasable and programmable read-only memory. What does it mean? Here, data can be erased. Data can be erased, but for erasing the data, we need UV light rays, and up to the duration of 40 minutes. During the programming, here electrical charge is trapped in insulated gate. The charge is retained. The charge can be retained for more than 10 years because the charge has no leaking path, so it can be stored for 10 years. For erasing the charge, ultraviolet light is passed through quartz crystal window. So during normal use, the quartz lid is sealed with a sticker. Next is EEPROM, electrically erasable and programmable read-only memory. EEPROM is programmed and erased electrically. Here we can erase in our last slide, as we can see here, ultraviolet lights are used for a duration of 40 minutes to erase the data. But in EEPROM, the data can be erased electrically. It can be erased and reprogrammed about 10,000 times. Both erasing and programming take 4 to 10 milliseconds. In EEPROM, you can erase the data according to your selected location. It is not necessary that you can delete the whole data. You can select a particular set of data that you want to delete, and you can delete by exposing it into electrical signals. So EEPROM can be erased one byte at a time rather than erasing the entire chip. Next comes flash memory. Flash memory is similar to EEPROM. It reads the content of a single cell but write the content in the block forms. So it will read only cell by cell content, but when it will write a complete block, and block consists of cells. So flash drive basically have greater density as they have higher capacity and low storage cost bit. Power consumption in flash memory is very low. That's make it basically attractive because less power is needed. Single flash chips are not sufficiently large, so large memory modules are implemented using flash cards and flash drive. So this is the basic diagram of a RAM chip. Let's understand this diagram first. The chip, the size here, the size of the RAM is 128 into 8. So what does it mean? 8 mean? The 8, that means we have a 8 bit of data on data bus. So we need for data 8 bits. So here, because of this 8-bit data bus is used. Okay. In RAM, we can read data, we can write data. So we can read data and we can write data. These are read and write signals. If we want to read the data, we need an address. If we want to write a data, we also need an address on which location we want to store our data. So these are address bit, and address bit will be carried by your address lines, address bus. So what will be the size of address bus? This first part, that is 128. 128 is equals to 2 to the power 7. So size of address, the number of address bit needed will be 7. That's why we wrote 887 here. Is it clear that it is read, write? Why 8-bit data bus? And from where we got 87? Then CS1 and CS2 complement. The function table specifies the RAM chip unit. When we have CS1 is equals to 1, when the value of CS1 is equals to 1, and when the value of CS2 is equals to 0. When the value of CS2 is equals to 0, then the value of CS2 complement will be equal to 1. When both the values are 1, the memory will be in inhibit state and it is in high impedance state. The data will be high impedance state, said the data will be there, but you cannot do anything. When the value of CS1 and CS2 complement is 0, memory is in inhibit state but also in a high impedance state. But when the value of CS1 is equals to 1, then we can input data to RAM, output data from RAM. We can read and write data when the value of CS1 is equals to 1. We can only read or write data in RAM when the value of CS1 is equals to 1. And now this is the block diagram of ROM. So here the size of the memory is 512 into 8. So 8-bit data bus is there, and 512 is equals to 2 to the power 9. So the size of address bus will be equal to the 9-bit. So here it is written 89. Read and write signal is not there. Why it is not there? Because ROM can only read the data. It cannot write any data. So if we are getting CS1 is equals to 1. If we are getting CS1 is equals to 1, that means we are getting a read signal from CPU and the ROM will be active. The ROM will be active. But if the value of CS1 is equals to 1 and CS2 is equals to 0, the data, only then ROM will work. Otherwise, the ROM will be in high impedance state and you cannot read any data from RAM. So when the chip is enabled by the two select inputs, so these are the two select input using which the chip is enabled, the byte selected by the address line appears on the data bus. And when the ROM is selected, the byte appearing on the address bus goes to that address. On that address, we can read the data. Then what about memory address map? Here we are only learning about memory. So we have to map the memory. And what is the important term that I'm going to repeat again and again from my first slide? That is your address. So we have to map the address with the memory first. How it is mapped? Let's understand this. For this, I'm just directly going to my last slide so that I can explain it clearly. So I will discuss this topic in my next video lecture. That's all for today. Thank you very much.